All right, let's get started. So next we have Benedick Bunz, Chief Scientist and Co-founder of Espresso Systems, and also Assistant Professor of New York University, and also a PhD graduate from Stanford. I actually used to take a course from him as well. All right, let's welcome Benedikt.
Thank you very much, and yeah, thanks for putting this event on. So today I'm going to talk about why sharing is caring, and in particular why sharing a sequencer is caring about interoperability. So rollups are this beautiful technology, and what they allow you to do is they allow you to horizontally scale Ethereum. So I have an application layer service that executes transactions and proves state. So I have a bunch of rollups here. Each of them has a bunch of transactions. They execute them, and then they prove that they executed these transactions correctly. And this has several advantages. One of them is that it can shard the computation. So each rollup can process a different set of transactions, and the computational load for each rollup is completely independent of what the other rollups are doing. The other one is that powerful nodes can help weaker nodes verify the state. So the rollup server, a powerful unit, can basically prove that it did the computation correctly, either through ZK proofs or through fraud proofs, and then weaker nodes can assert that the computation was done correctly without having to redo the computation. So that's another scaling benefit. And then the third one that sometimes maybe is a little bit underappreciated is that you can have, or maybe it's not underappreciated, but you can have totally different types of computations and types of VMs. So you can have EVMs running on these rollups, but you could also have a risk architecture or some application-specific rollup, and so these systems can get significantly more parallelized. Unfortunately, though, these systems also have a significant downside, and this is mainly due to the fact that they're run by isolated sequencers. So the sequencers are the ones that choose what transactions get included into the rollup and in what order. And this has several drawbacks, and one of the main one is that the interoperability between apps across the rollups is limited. You would have to bridge assets or bridge things from one rollup to another first, which has some cost and latency. And this basically gives you a significant loss, and this loss is that you lose synchronous composability. So unlike on the layer one, you cannot have one smart contract that calls the next smart contract that calls the third smart contract if those smart contracts run on different rollups. It also fragments the liquidity. So, some funds that are used on one rollup, you first have to bridge them over to be used on another rollup, and this is bad in many DeFi applications in general. And this is incredibly problematic, especially if we think about what Ethereum and blockchains are really about. They're about their unity, not their fragmentation, right? The idea and the power of blockchain comes from the fact that everybody can use the same system and seamlessly interoperate on the system, and I can build a smart contract without knowing what all the other smart contracts are out there, and still users can use them together, they can chain transactions and all of that. So seamless interoperability of applications is the promise of trust minimized infrastructure, and what really differentiates Web3 from Web 2, where I have these isolated walled gardens. So what is this? So let's dig a little bit deeper of why this is and what the roll-up sequencer actually does. So in the roll-up sequencer, we have a bunch of users that submit transactions to the sequencer. Then the sequencer summarizes these transactions and produces state update plus a proof and posts that to Ethereum. Onto a smart contract, which checks the proof, or there's some fraud proof mechanism, it doesn't really matter, and basically accepts the state update. So the sequencer determines the rollups blocks. You can think of these things as blocks, and in particular it determines which transactions are included and in what order. So the sequencer could also outsource this job of selecting the transaction to some other party or to a mechanism. So for example, an auction. So it could, for example, have an auction mechanism where it basically says, I'm going to build the block that the highest builder, so-called builder that builds the block, I'm going to propose the block, or I'm going to post the block that the highest bidding builder is running. this, we can think of this as an auction, and this actually even happens within Ethereum itself, where this is called the proposer-builder separation. So there is this proposal, or there's been this proposal, it's been actually around for a long time, but it's sort of recently gained a lot of attention again, of base sequencing. So if you look at the first Arbitrum paper, for example, the original Arbitrum paper, it didn't have some separate sequencers. Users would send their transactions directly to the L1, and then the L2 node reads the transaction, the finalized list of transactions from the L1, and executes them to determine the state transition. And then the rollups would basically read, so the rollups would read and from the L1, and then basically just post the proof to the L1 that the state update was done correctly. So this has some advantages, this old sort of original version, which is that, first of all, it inherits the security properties of the L1. So we believe the L1 is incredibly secure. So this system should also be secure. It should be, for example, much harder to censor transactions using such a based rollup versus a centralized sequencer. But it also can have improved interoperability, not just between rollups, but even between rollup applications and the L1 applications. Why is that? Well, the person, now the L1 leader, the L1 proposer, gets to post these transactions to the L1, and it could sort of interleave them with other L1 transactions. So it could, for example, say, okay, I'm only going to, it could give a user a guarantee that here this rollup transaction will execute if and only if this other L1 smart contract transactions will execute. However, so why did we move away from that? Well, let me first talk about this. So ultimately, users want a secure, convenient, and low-cost experience, right? And satisfying the user's intents will be most efficient across applications deployed to rollups with the greatest unity, not only with each other, but also with the smart contract of L1. So this based sequencing is really, it seems like the goal, right? So why do we move away from this idea? Well, well, we'll get to that in a second. I just first want to talk about, how a proposer can promise user atomicity. So this is the concrete example. So user says, I want my transactions on 2 rollups, or a rollup and an L1, to be executed atomically. Right? I want to buy one asset on one rollup and sell another asset on the second rollup, but they only want these things to happen at the same time, not one or the other. And the L1 proposer can promise this. It says like, I will do this, and then it creates this super block. It signs it, posts it, and posts it to the L1. And it can even economically stake funds behind this promise. So it can back up its promise. First of all, it could put its reputation behind it. Maybe that's not that useful, but it could even say like, I promise you this, and if I don't do this, I will get slashed. Okay? Because you can afterwards verify whether both transactions actually executed at the same time. And this is how this shared proposer can give economically backed promises to users. It can satisfy users' intents or back them up economically. And the user knows that, well, the proposer likely does not want it to get slashed, so will honestly execute this transaction. So what happens in a scenario where we have these shared proposers? So say we now have a builder that wants to try to satisfy some promise over 2 rollups that have different sequencers. Well, now it can promise that, and if not, it still says the same thing. I promise that, and if not, you can slash me. But the problem is that, now it builds 2 blocks. It builds a block for rollup A and a block for rollup B. But the problem is maybe rollup A accepts its block, but rollup B doesn't. So even without any fault of the builder, one block got accepted and the other one doesn't. So it couldn't satisfy the promise, and then it will get slashed. So to be honest, no rational builder would actually try to provide this, because it simply cannot give this promise, right? Even if everybody is honest here, it cannot give this promise of atomic execution. So this leads to this topic of proposer promises, or pre-confirmation, which is that a shared proposer for a bundle of multiple rollups can do a bunch of things. It can provide these fast pre-confirmation, it can coordinate message passing between ZK provable chains, something like the Polygon ACK layer, and yeah, it can do a bunch of really cool things, and all of those have one thing in common, is that if it fails to achieve its promise, it will get slashed. So these are all economically backed promises. It can also, there's a bunch of other cross-domain user intents. One of the simplest one to think about is just sort of bridging funds from one chain to another. This is, like there's much cooler things you can do, but even just sort of fast bridging between one rollup and another. So I send some funds on a bridge on one rollup, and I want to receive them on another. That sort of, already captures a lot of the power of these cross-rollup intents. So why aren't we running base sequencing yet? What is base sequencing missing? Why were external sequencers introduced? Well, one of the main reasons is for efficiency. It has, so if you remember the base sequencing, the original base sequencing proposal, every single transaction needs to get posted to the L1 and as an individual transaction directly by the user. External sequencing has much better data compression, so significantly lower DA costs. In external sequencing can collect transaction, it can strip the signatures over time, and can optimize it when to post them to the L1. It also can give fast, low-risk pre-confirmation. So L1 block proposals risk being dropped or reorged before the 15 minutes have elapsed. An external sequencer can pre-confirm pure L2 transactions by just saying, like, yep, I included this, and if you trust the sequencer, then you know this will happen. And it can include these transactions, especially the ones that do not depend on unfinalized L1 transaction. So is there a middle ground? So can we basically achieve the benefits of base sequencing, this shared proposing, while still having the nice data compression properties and sort of the nice pre-confirmation properties that an external sequencer gives you? And the answer is yes, base sequencing 2.0 with an external finality gadget. So the idea is that we put something in the middle here between the layer 1 and the layer 2. So now the users will submit their transactions to the L1 proposer still, but the L1 proposer doesn't post it on the layer 1. It instead posts it to a fast finality gadget, where L1 validators can opt in. So this has much faster latency, so something like less than 5 seconds. And once the transactions are included on this finality gadget, then you know the order of the transaction. So all the finality gadget does is it agrees on the order of the transactions. But once I know the order of the transactions, the state transition is deterministic, right? If I know the order of the transactions, everybody can just execute them and knows exactly what the list of transactions is. So rollup smart contracts on the L1 need to require that the transactions are first confirmed by this fast finality gadget, which is just a BFT consensus protocol operated by, and you can have you can have it be operated. Well, I cannot go back. One thing, you can improve the power and the security of this L1, this fast finality gadget, by having the L1's validators participate in this finality gadget. So they also sign off that they've seen this order of the transaction and they agree on it. And you can have L1 composability. So if the L1 proposer still proposes this block, they can then build L1 and L2 blocks at the same time, right? So they can satisfy user intents both over L1 transactions and a bunch of L2 transactions. You also have something called conditional finality. So the finality of any L2 transaction is conditioned on the finality of the most recent L1 blocks. It depends on. So if the last, if the L1 block forks, well then, you need to fork also all the L2 transactions. But if the L1 block becomes final, then you already know the next set of L2 transactions because they were confirmed by this finality gadget. Okay, So what else is base sequencing missing now that we're used to roll-up sequences? One of the important things is the MEV capture for rollups. So enshrined rollup sequencer have additional revenue beyond the gas fee in the rollup, which comes from tips that users pay for intent satisfaction. So even just wanting to be first in a block. So they pay these priority tips. So vanilla-based sequencing is not economically aligned with the rollup. So in vanilla-based sequencing, the L1 proposer gets to order all of the transaction. So they get all of the MEV fees, right? Versus the rollups now get none of this. So what we're proposing is a mechanism to redistribute the sequencing MEV back to the rollups. So how do we do that? Well, what we're going to do is instead of saying instead of basically saying the L1 proposer directly gets to propose this block, what we're instead going to do is run this auction mechanism. So we run some public auction where basically we auction off the right to create the superblock for the shared finality gadget. So there's multiple proposers that compete for getting the right to update all the rollups, or a subset of them, right? You could bid on, say there's 5 rollups or 1,000 rollups, but let's focus on 5. You could bid on I want to build the block for 3 of them because I know that I can satisfy user intents over 3 of them, and then someone else bids on the other 2, or people bid on individual ones. And this shared revenue, so what we're proposing here is having one auction for all of these rollups, where you can, so basically a marketplace to become the shared sequencer for all of the rollups or a subset of the rollups. This can actually be better for everyone involved than what we have than having separate auctions for all of the rollups. Why is that? Well, the problem with having these separate auctions is that as a proposer, I don't know whether I will win, I cannot satisfy these users' intents because I might win one of the auction, but not the other auction. Here, the shared auction mechanism allows me to bid higher on bundles of rollups because I know that I can extract or I can provide more value for a bundle of rollups. So how do we do this? There's many analogies to this. You could think of this as a music festival. I've heard that, so say we have a music festival and we have a bunch of bands, and the question is one challenge with this shared auction is how do we now split the revenue amongst the different rollups? So say we sell all of them together, how do we split the revenue amongst all of these rollups? Well, the analogy of this is say a music festival where we have a bunch of bands, right? And the music festival makes some money, but how does it split the revenue amongst the bands, right? How does it know, this one band was sort of significantly more important than the other? You could try to figure out some custom backroom deals, but you could also run a so-called combinatorial auction. So the way that a combinatorial auction works that basically proposers can bid on any combination of specific rollups. So they could, for example, bid on the individual rollups or the bundle, and then using this combinatorial auction, we can actually figure out how much each rollup would have gotten on their own, right? Because that's just the bid on, people will still bid on the individual rollup, so we know exactly how much a rollup was worth on their own, and we can use that to distribute the revenue from the entire combinatorial auction. But wait, how is this base sequencing? What about the L1 proposer, right? So here we have this auction, a bunch of people participate there, but we've completely sort of lost sight of the L1. This sort of allows you to bring shared sequencing to all of these rollups, but we wanted base sequencing where we can even have interoperability with the L1. And the idea is that after we run, so the idea to bring basically the L1 proposer back, so base sequencing 3.0 sort of, is that after we run the combinatorial auction, we allow the L1 proposer, so we run a combinatorial auction, let's say sometime in advance for some slot, let's say tomorrow. And then the L1 proposer, there's some look ahead in Ethereum, so we know exactly who's going to be the L1 proposer for that time period. And what they can do is they can purchase the proposal right for any bundle at the winning bid. at the winning price. So say a bundle costs, I don't know, 10 ETH, then they can buy it for, they can pay 10 ETH plus some premium, so maybe, I don't know, 11 ETH, for the winning bundle. So they can basically buy it back. They uniquely have the right to buy it back, which allows them to guarantee that they can build these shared blocks that include both the L1 and everything else. So what is shared sequencing after all? A marketplace, you can really think of shared-based sequencing as a marketplace. It's a marketplace where proposers can buy and sell block space on different rollups and the L1 itself. And why would they do that? Well, because buying this block space and buying these proposer rights allows them to satisfy user intents across many different rollups, which is both better for the users, but it's also better for the proposers because then they can, charge fees for satisfying these intents. Okay, so thank you very much. That was the talk, and yeah. The egg layer, no, I think that, for example, the egg layer is actually incredibly compatible with this marketplace because it allows you, so first of all, what you could do is, you could say the Polygon chains, want to be always sequenced together, then they could enter the market as one unit. Sort of saying that, all the Polygon chains are going to be, always sequenced together, and they get, you can only bid on all the Polygon chains together. And this actually makes it very compatible with something like egg layer. And also egg layer, egg layer allows this shared proving, right? Which is sort of on a different layer. It's on a different level, and it becomes actually more useful when there's a marketplace where you can buy the proposing rights for many rollups at the same time. So, but yeah, I think that's. I think what's more important is having one marketplace. Like the fast finality gadget, it's more useful to have one fast finality gadget because then if I have one fast finality gadget, I know that the transaction is final on 2 rollups at the same time. So I can, for example, then immediately accept some bridging transactions, right? Because I know that even if the finality gadget reverts, it will revert on both of them. What is more useful is, yes, to have one marketplace. I do agree that one marketplace is better, but I think that maybe there's as I said, you could have sub marketplace and then sell the super rights, but yeah. 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 Thank you.
Yeah. Thank you.